But for your all's information, I am going to go ahead and record it, because by recording it, I can have it available as, I think it's an MP3 or 4 form that I could potentially send to people later. And I don't know how long it takes to have the transcript prepared and have the thing rendered. But anyway, I am recording it, just so you know. So what I want to do is I want to kind of do a little mini lecture type of thing. And right now you should be able to see my document camera. Can you guys?
I can.
Okay.
Yes.
So I want to do a mini lecture. It'll probably take me about maybe 30 minutes, and then I'll answer questions. Unless you think it's really important, don't interrupt me, just because it will, I believe, be easier if I just keep it rolling. Think of me as, you know, your lecturer, and you're sitting there in class. Interrupt me if it's a really important point or you think I've made a mistake. But save most of the questions to the end, okay? So chapter 3 is an introduction to probability. We'll be dealing with probability for 3 chapters. And in this case, the first chapter deals with 3 basic topics that I've kind of summarized here. The first is classic probability, and I'm going to also include empirical probability. The difference between those things is where you got the data. So in classic probability and empirical probability, you essentially get the probability by determining the number of ways a specific criteria is met and divide by the total number of possible outcomes. So the simplest example I can think of would be like rolling a die. The probability of rolling a 1 on a 6-sided die is 1, because there's only one value of 1 on the 6-sided die, right? Divided by 6, because there are 6 different numbers on the die. It's pretty straightforward, right? When you're talking about empirical probability, you actually are getting your data from a repeated experiment. So an example of this would be something like free throw percentage. Okay, so if you look at free throw percentage, or in baseball, I forget what you call it, but anyway, the probability of hitting a free throw can't be done in the same precise way as this, because I mean, you know, it just doesn't lend itself to this kind of specific clarity. However, you can estimate the probability of someone throwing a free throw and getting the point by taking the number of free throws they've made in their career or their time playing basketball, divide by the number of opportunities, right? The number of times they've gone to the line. And that gives you an estimate of the likelihood of them making the next free throw, okay? So that's pretty straightforward. The other 2 topics that are in this chapter are, and they're not in this order actually, I think the chapter deals with the multiplication rule first and then the addition rule. But knowing which of these 2 rules to apply is very important, because the formulas for both of these rules are on your formula sheet, but you have to be able to decide which one's appropriate. So the clearest way of stating it is that when you have a problem that should be addressed using the addition rule, it's because there's a single event or selection, and the connecting word has to be or. Something like if I were looking at a class and I noted all the people who were of a certain gender and all the people and their color of hair, okay? I could ask, what is the probability that if I randomly select someone from this class, I will select a woman who has blonde hair? I'm sorry, I didn't mean to say that. A woman or someone who has blonde hair. Now that's a case that clearly is the addition rule, because I made a single selection of one person from the class, and the connecting word was or. Now the multiplication rule is different, but you can always tell a multiplication rule problem because the significant fact is that it must deal with more than one event occurring sequentially. So something like, I am dealing myself out a hand of cards, right? What's the chance that I will deal out a queen followed by a king followed by a two? Questions like that, okay? And so the tell is that there is more than one event occurring, one right after the other. So that's the three basic topics that we want to deal with. But to deal with those topics, we need to really understand the nomenclature. And by that I mean the little shorthand that we use in writing these things. So this may not give you guys any problems at all, but it really is problematic for a lot of people. So the notation looks like this in its simplest form. And this means the probability of an event called A, okay? Now, what happens is people know they're in a math class, so they think algebra, right? And so they're thinking, okay, this is a capital P that means something, symbolizes something, times an A. It's not that at all. There is no implied algebraic form here. It's just capital P always represents probability. And the event that you're trying to find the probability for is what appears in the parentheses. Okay, now it's important to know the notation because it's used on your formula sheet for the formulas for each of these, topics. Okay, so there is one form that's really confusing, and for a lot of people who don't listen to this tonight, this is going to be a problem for them, I guarantee it, on the lab assignment due tomorrow night. When you say probability of A and B, it can mean two things, but it really shouldn't. When it's like this, you always assume that it's a single event. So this actually means what is the probability of a single selection which contains both conditions A and B at the same time. So like with that class, if I took note of everyone's gender and everyone's hair color, I might ask, if I selected one person at random from the class, what's the probability that I get a woman and a blonde? That would simply mean what is the chance of me in that single selection getting a blonde-haired woman? Now, it confuses people because they confuse it with the multiplication rule, but because the multiplication rule requires multiple events, to indicate a multiplication rule problem, it really should say, if two events or selections are made and they occur sequentially, so you pick one and then you pick another, then in that case, it really shouldn't have been written probability of A and B. It really should be written probability of A occurring and then B occurring. Okay, but most of the time, most books leave out the word then. But you can tell the difference because it must state that it's multiple events if it's going to be a multiplication rule problem. So on your assignment that's due tomorrow, I'm just going to read one of them off the fourth problem. No, maybe it's the third problem. It says, if two people are randomly selected, find the probability that they are both left-handed and women. Okay, so that would mean what's the chance that I will pick a left-handed woman and then pick another left-handed woman in the second event. So this idea of knowing whether there's more than one event occurring sequentially is really important in understanding the notation. Another notation that people have a lot of trouble with is this notation, which is a conditional probability notation. Now, this is supposed to be a completely vertical bar. I know it probably doesn't look like it, but what this says is find the probability of event A happening given that. That's literally what the vertical bar means, given that. So let me read it again. Probability of A happening given that B has already happened or is known. Okay, now, the reason you would need conditional probability, sometimes it doesn't matter, right? So there are events that are inherently independent of one another. But conditional probabilities are needed if the occurrence of the first event affects the probability of the second event. So let's say that your kids are sitting there and you're handing or you're passing around a bowl of candy, right? And there's 4 red candies, 3 orange candies, and 1 blue candy. Well, the first person takes a candy, pops it in their mouth, they've already changed the probability of getting a certain thing in the next go round for the next person. So the probability is, what do I have? 3 greens, okay, 3 reds and a blue, okay. So the probability of the first person randomly selecting a red candy, let's think of it as, you're reaching your hand in a bag, so you don't know what you're going to get. The probability of getting a red is 3 out of the 7 candies that were in there. But once that is taken out and is put in the mouth of that person and the bag goes to the next person, the probability that they will bring out a red candy is now 2 out of 6, because there are only 2 red candies remaining in the bag, and there are only 6 candies in the bag. So conditional probability is necessary in any case where you are dealing with the multiplication rule and doing one thing actually affects the probability of the next event. It doesn't always. So let's talk about a couple of very important ideas in probability. So in the addition rule, the important idea is whether or not the events are mutually exclusive or not mutually exclusive. And all the phrase mutually exclusive means is, can they happen at the same time? So I've got a very simple example here. So if you think about a 6-sided die, then if I wanted to know the probability of rolling a 2 or a 3, those 2 events are mutually exclusive because you can't both roll a 2 and a 3 at the same time. Okay? It's either one or the other. You can't do it at the same time. However, same setup. I'm rolling a 6-sided die. If I wanted to know the probability of rolling an even number or rolling a 4, those 2 things are not mutually exclusive because a 4 is an even number. Okay? So you have to consider mutually exclusive conditions when you think about the addition rule. When you are doing something with the multiplication rule, you have to think about a different idea, and that's independence. And independence is this idea of whether or not the occurrence of the first thing can affect the probability of the second thing. So there are some very common naturally independent events. So if I wanted to know what is the probability that in 2 pregnancies I'll have a girl and then another girl, the probabilities are mutually independent of one another. Having a girl in one pregnancy cannot affect whether you have a girl in the next pregnancy. I mean, this is actually a very common misconception by people that if they thought about it, they'd understand that it can't be true. But I can't tell you how many times. I have 3 daughters, okay? I can't tell you how many times people have said, now, if you have another baby, you're probably going to get a boy because you've got 3 girls. Au contraire, it's still 50-50. It's actually not quite, but close to 50-50. The events that preceded it cannot affect that current event. Or, for example, if I wanted to know the probability that if I rolled a 6-sided die, I would roll a 3, and then I flipped a coin, I would flip a head, those 2 things are also independent. The rolling of the dice cannot affect the flipping of the coin. But there are a lot of things we deal with that are not naturally independent. So a good example is this idea of dealing out cards. So if you deal cards and you want to know what is the probability that if I deal out 2 cards, I'll deal out a 10 and then a king. Now I have to go one step further and I have to ask, am I dealing the cards with replacement or not with replacement? If you deal with replacement, what it means is that you deal the first card, you look at it, you know what it is, and then you put it back in the deck, shuffle the deck, and now you deal the second card. Replacing that card into the deck returns the deck to its original condition. And doing that guarantees that the next event will be independent of the first event. In fact, we say, what I've got written down here, independence is guaranteed if you sample with replacement. But most of the time in this situation, we do not sample with replacement. So let's do it both ways. So if you had with replacement, then the probability of roll or dealing out a 10 and then a king is simply the probability of dealing a 10 times the probability of dealing the king. So the probability of dealing a 10 is 4 out of 52 because there are 4 10s and 52 cards. And then I take that 10, I put it back in the deck, I shuffle the deck again, and now I deal a second card out, and the probability of it being a king is 4 out of 52 also, because again, there are 4 kings and there are 52 cards. Now, this is one of those answers that is problematic for most people, so I want to actually turn on my calculator and show you this. Okay? You should basically always do this on the calculator, because a lot of times the answers that you might be asked to answer as a fraction, and most of you guys are not good with these things. So just do parentheses 4 divide 52 times, whoops, sorry, apparently I've got an extra parentheses there. Okay, parentheses 4 divide 52 times parentheses 4 divided 52. There's my answer as a decimal number, and then hit math, enter, enter, and there's my answer as a fraction. The completely reduced fraction is 1/169th. Okay, but what would this have been if I were sampling without replacement, which means I deal the first card, but I leave it sitting there on the table, and then I deal a second card. So in that case, the way that should be written is, and I'm putting in the word then. A lot of times they don't. A lot of times they just put capital P parentheses 10 and king, you know. So that is the probability of dealing the 10 out in the first dealt card times the probability of dealing a king given that I've dealt a 10. Now, that is not the same as the thing above, because this second part is the conditional probability that's based upon the change in the deck created by dealing that first 10. Okay, so dealing out the 10 with the first card, of course, is still 4 out of 52 times, but dealing out the king is different because, yeah, there are 4 kings, so that goes in the numerator, but now there are only 51 cards. Okay, so in fact, the likelihood of dealing out a king now has slightly improved because there are fewer cards to choose from. So if I do that on my calculator, 4 out of 52 times 4 out of 51, notice you can compare the decimal numbers to see this, but notice that the probability when you sample without replacement is slightly higher than the probability of doing it with replacement. Okay, and I could get that as a fraction. It's 4 out of 663. Okay, so with all that, let me do a problem and ask several different types of probabilities based upon this problem. This problem actually looks, it's not the same problem as you have in the last, that long page problem 3 or 4 on your homework assignment, but it's close. So this thing is called a contingency table here. It's actually just this part. What it does, all contingency tables pit at least 2 characteristics against one another. So in this case, it's gender versus whether or not you wear glasses. Okay, and contingency tables cannot be any smaller than 2 by 2, but they can be bigger than that. So if I look at this row, it represents all the men. And when I add the men who wear glasses to the men who don't, I have 50 men. This row represents all the women. So 15 of them wore glasses, 35 did not. That adds up to 50 as well. Now, this column here are all the people who wear glasses. There were 20 men that wore glasses, 15 women that wore glasses, for a total of 35 people wearing glasses. And then in this column, everybody doesn't wear glasses. And so there were 30 men who don't wear glasses, 35 women who don't wear glasses, for a total of 65. And then if you add up the row totals or the column totals, you get the grand total. And in this case, it's 100. Because, of course, I made one that had really simple math. Okay, so if I'm simply asked, what is the probability that if I select one person, now remember, if it's written like this, the assumption is that it's only one person, okay? So if I select one person, what's the probability that they'll wear glasses? Well, that's just the number who wear glasses divided by the total number in the sample, okay? So the number that wear glasses is this 35 out of the total of 100. Okay, so that's pretty straightforward, okay? Then this next one says, okay, what's the probability that when I make a single selection, I get a man and glasses? In other words, a man who wears glasses. Okay, so this 20 are the men who wear glasses. All right, so there are 20 men who wear glasses, so it's 20 out of the 100. Now, it seems like the next one is similar, but it's not exactly, because this is a conditional, and it says, if I select one person, what's the probability that I will select a man, given that I know I selected someone who wears glasses? What this does is restrict the answer to only people who wear glasses. So conditionally, if I'm restricted to only the people who wear glasses, there's 35 total people who wear glasses, and 20 of them are men. Now, for a lot of people, this is the toughest thing. But what you should think about is that if I have a conditional probability with a contingency table like this, all this second thing does is it determines the denominator of the fraction, because it limits the denominator to only those people that have that condition. Okay? Okay, so the next one is, what is the probability if I make a single selection that I select either a man or someone who wears glasses? Now, I want to show you on your formula sheet how they write it, okay? So here it is, the probability of A or B, okay? And I just deal with the full rule. This second rule is for only mutually exclusive events, but if you use just this full rule and the events are actually mutually exclusive, then this subtracted part is always 0 when the events are mutually exclusive. But you notice what it says. It says the probability of A or B is the probability of A added to the probability of B minus the probability that A and B occur at the same time. And that's because there's a fundamental rule in probability that you cannot count any selection more than once. Okay, so in this problem, it would be the probability of selecting a man added to the probability of selecting someone who wears glasses minus the probability of selecting a man who wears glasses. Okay? So, the probability of selecting a man, there are 50 men out of 100. Add to that the probability of selecting someone who wears glasses. Well, there were 35 people that wore glasses out of 100. And I have to subtract out the probability of selecting a man who wears glasses, because notice that when I selected a man and then I selected someone who has glasses, I counted these 20 people twice. They counted in both the row and the column. You can't have that. So you have to subtract out the 20 men with glasses who were counted twice out of the 100. So since this is the same denominator, I can do that addition and subtraction over that common denominator. So 20 plus 35 is 85. 50 plus 35 is 85. Minus 20 is 65 out of 100. Okay, now if there had not been any men who wore glasses, this subtracted part here would have been 0 anyway. So if it's mutually exclusive, that subtracted part falls away because nobody could have both characteristics at the same time. Okay, and then finally, if 2 people are selected, now I know I'm dealing with the multiplication rule. what is the probability that I'll select a man and then another man? So again, you have to envision that these people all have their name and their gender and whether or not they wear glasses on a piece of paper, and you just throw them all in a big hat, and then you pull out one and then you pull out another. So this is the probability of selecting a man with the first selection, and then the probability of selecting out another man given that the first one was a man. Now, these are not independent events unless you sample with replacement. And if it's not told to you, you assume that you're sampling without replacement. Okay, so sampling without replacement, and I think on your homework lab assignment you have to do it both ways, but without replacement, it would be, what's the chance of selecting a man? Well, there were 50 men out of the 100. So that name is just set down on the table and you walk away, and now you go back to the hat and you pull out another card. What's the probability of selecting another man given that the first person was a man? Well, here's what you have to know. Since that guy's name is sitting on a table, there are now only 49 men in the hat, right? And there's also only 99 remaining selections. Again, it's because a piece of paper with a man's name out of the 100 has been selected in the first go and set aside. Now there's only 99 names in the hat and only 49 of them are men. And so this is your multiplication here, and if I do that on the calculator, it's 50 out of 100 times 49 out of 99. And there's your answer. And this would be one of those places where I would probably just go ahead and show it as a decimal number, either 0.245 or, 0.247 or 0.24575. If 4 or 5 decimal places should do it, unless it's a tiny probability that starts with a bunch of zeros. Okay? And then finally, and after this, I'm going to let you ask me questions if you have any. You cannot say that the probability of any event equals 0 unless it's impossible, unless it cannot occur. Because that's what a probability of 0 means, that the event is not possible. So let's say that you wanted to know what's your probability of winning a lottery when 10,000 lottery tickets were sold. Okay, so if you have 10,000 tickets and only one winner, your chance of winning is 1 out of 10,000, right? Because you only bought one of those tickets. And if you do that on a calculator, that, and I'll just show it to you, 1 divided by 10,000. That is going to show up as a scientific notation. And we talked about this yesterday for people who were in there. And that really is the decimal number. Put a decimal place, 1 less 0 than the number it shows you after the E, and then the rest of your number, which in this case is a 1. Now, if you had said 0.000, because that's the way it rounds, right? I wouldn't have been wild about that, but I would have accepted it as the correct rounding to the 3rd decimal place. That is a very tiny probability, but it's not impossible. So please don't ever say that the probability of something occurring is equal to 0 unless you really mean that that event cannot possibly occur. Okay, ladies, do you have questions? I see Sarah's unmuted her mic. Diane, you have questions? If you don't, that's cool with me too.
Yeah, I had a question while going through the book, the notes in there, and kind of while doing the lab assignment, but I think you addressed it. It was, I'll give the question from the lab assignment. It was basically like one of the ones you just did where it said if two students were selected without replacement, what was the probability that they would both prefer the same kind of book? And when I did it, it gave me like a scientific notation number. So in that situation, should I do a fraction?
No, just move the decimal place.
Okay.
The technical rule is that you move the decimal place the same number as the number after. Okay, let me just show you an example. Okay, so if it says this, okay, technically you move the decimal place 5 places, okay? But notice that when you move it, the first decimal place just takes that first number out, right?
Yeah.
All the empty loops get filled in by zeros. So now what I just tell people, because sometimes it's easier for them just to see, that if that's a 5, it means there's 4 zeros in front. The decimal point, then 4 zeros, and then the original number.
Okay.
Okay? Yeah, you have to be able to convert from scientific notation.
Okay.
You do not need to express that as a fraction.
Okay, perfect.
Okay, either the other of you have questions?
I do. So back to where you had said that the 0 was impossible. On our lab, there is a question, and it was, I believe it was
about art students, right?
Mm-hmm. Yes.
Yeah.
That
Nobody
0.
said they preferred art. Therefore, there were 0 over however many there were, 50, something like that.
Yeah, I think so.
Right? Because nobody said art.
50. Yeah.
So there would be 0 over the 50, and that does turn out to be 0.
Yes.
So
Okay.
impossible, because no one in the survey said they preferred art books.
Okay.
Period. Full stop. It's just like, do you remember the candy example I showed you where there was 1 blue, 3 greens, and 3 reds? If I ask you what is the probability of sequentially pulling out a blue and then another blue, well, that's 0, because there's only 1 blue. Once it's gone, it's gone. So it is impossible to pull out 2 blue candies if you sample without replacement. You see what I mean?
Mm-hmm.
Now, the chance of doing it with replacement, so without, it can't be done. With replacement, it could be done, right? Because it is the probability, okay, and then another blue. It's the probability of pulling out a blue one times the probability of, again, pulling out the blue one. But you put the blue one back in to the bag. So that would be 1 out of 7 times 1 out of 7, which is 1 out of 49. So that's possible. So you see why the multiplication rule in some ways is simple and in other ways complicated. You do have to make 2 decisions with the multiplication rule. First, you have to know that you need the multiplication rule, and that you get that really easily on knowing whether it is actually more than one event being considered one after another. And the second thing is you need to know whether or not the events are independent of one another. And a consideration in making that decision is whether or not you're sampling with replacement or not with replacement.
So I know I may just be really numb in this, but the probability of occurrence of both events A and B versus the probability of the occurrence of either A or B. So one is you're multiplying, the other is you're adding and then subtracting. if in our lab in question 2, there are 4 parts to that question, all of them are the probability of occurrence of both events, unless I'm missing something.
Well, they're all multiplication rule problems.
Yes.
Okay, but the first one is without replacement.
Right.
So the probability of the second is affected by the occurrence of the first.
Correct.
Okay. The next one is also without replacement, but the difference between the two is in the A part, both the numerator and the denominator of the second probability have changed because it's asking you about the same type of book.
Mm-hmm.
In the second one, only the denominator changes because the type of book has changed between the two. It's very similar to this thing here. Okay, because the numerator here in this problem didn't change because all the kings were still in the deck because the first thing dealt was a 10. But the denominator changed because there was one less card. So similarly in 2B, there are one less in the group of 50. When you make
Right.
the first selection, you take one out.
Right.
Right?
Yes. However,
So the denominator, the total in the denominator changes.
right, but the numerator isn't the same because one's asking mystery books and one's asking true crime.
Exactly.
Okay.
But all of the true crimes are still there.
Correct. Okay.
Right? You see what I mean?
Okay.
Then you have essentially the same problem except sampling with replacement or the C and D parts.
Right. Okay.
Okay?
Yep. Thank you.
Okay, ladies, I'm out of here then. Several other people had emailed me and said they were going to watch this and didn't. So probably I will simply reward you guys some extra credit for doing it. But if you know anybody else in the class that will want the little video, feel free to tell them that I'll try to have it available. But I probably won't have it available before the deadline tomorrow, but I will try to have it available. I'm not the one that renders it up to a video, okay? So I don't control the speed there.
Well, thank you for your time. I appreciate it.
Not a problem. See you guys.
Thank you.
Bye.